Hello everybody, it's Mr. Ray here with our next lesson in grade 11 University Math. We are working in the trigonometric function unit. So we've looked at the graphs and the functions for cos x and sin x, and we've recently applied transformations to them to alter their appearance and characteristics using the familiar transformation parameters a, k, d, and c, which work the exact same way as they did for the other base functions we did earlier in the course. Now we're going to extend into connecting the characteristics and looking at a graph and determining its equation based on the properties. So let's look at some of the stuff we have here. Okay, so the key concepts for today. If you have an equation with some transformation parameters for either sin x or cos x functions, so if you know the a, k, d, and c values, from those you can get the amplitude, the period, the phase shift, and the vertical shift of these sinusoidal functions. By the way, sinusoidal does not just mean the sine graph, it also means the cosine graph. So any graph that's in the shape of a sine wave, which is the sine curve, is called sinusoidal. Okay, so if I want to know the amplitude, I know I can get that from the absolute value of A. If I want to know the period, I know that's 360 degrees divided by whatever K is. The phase shift is equal to D, and the vertical shift is equal to C. And I can get that from either the sine or cos equations. In terms of the domain range, both of any sine or cosine function, the domain is all real numbers. It extends infinitely in both directions. And in terms of the range, it depends on the maximum and minimum, which you can derive from the values of A and C. And if you had any piece of a graph that shows a complete cycle or period, you can figure out the range, because that'll tell you the highest and lowest values within one cycle, which is the same for the entire graph. Okay, and we can use these transformations to model if we want to make a sine curve have different properties, like change the period, change the amplitude, change the max and min values, change the phase shift. We can now do that through taking a graph, taking the base function sine or cos, and applying all those transformations we've looked at last lesson. The key thing we're going to do today, and I have a couple of worksheets to practice this in a little more detail, is if you have a graph of some kind of sinusoidal function, determine its equation. And we're going to learn that there's not just one equation that's going to fit a given graph. There's going to be quite a few different equations that you could give to create that graph. So unlike going the other direction, if I have an equation, when I create its graph, well, there's only one correct graph for that equation. But if I have a graph and I want to create the equation, there's multiple correct answers. So we'll talk about that when we do the examples. And this is kind of repeating from the last lesson. Basically, it defines these parameters A, K, D, and C and what they're responsible for. In terms of the amplitude for A, the period for K, the phase shift for D, and the vertical shift for C. Okay, and anything that we just talked about, we tend to use the sine function as the example, but the exact same things happen with cos, okay, in terms of the transformation and characteristics. Okay, so let's go through a few examples just to get a hang of this. Determine the transformations that must be applied to the graph of f of x equals sine x, to obtain the graph of g of x equals 4 sine 3x plus 1. Apply these transformations to sketch the graph of g of x. Okay, so we're starting with g of x equals 4 sine 3x plus 1. And just to make this crystal clear, I'm going to put brackets around the 3x. And from that equation, I can extract the values of a, k, d, and c. I can see that a is equal to 4. I can see that k is equal to 3. I can see that d is equal to 0 because there's nothing with x in terms of being subtracted or added. And the value of c is 1. So I've got all my parameters. Okay, now in order to, if I wanted to change the graph of f of x into the graph of g of x, what would I have to do? Well, I basically go through this recipe of transformations here. We always handle the a and the k values first, followed by the d and c. It doesn't matter within a and k what I talk about first, and it doesn't matter which order I do the d and c, but it matters that the d and c come last. Okay, so the first thing I'm going to look at for me is the a value. The a value is 4. That tells me there's a vertical stretch by a factor of 4. Okay, and that handles the a value. There's no negative sign, so there's no reflection. K equals 3. Remember, the actual factor for that would be 1 over k, so 1/3. 1/3 tells us that it's a compression, horizontal compression, by a factor of 1/3. Okay, that handles the k value. The d value being 0 means there's no horizontal translation involved or phase shift. And c equals 1 tells us there's a vertical translation. One unit up. Okay, so those three transformations will turn the graph of f of x, which is just sine x, into our transform graph for sine 3x plus 1. All right, so let's do a little sketch of what this looks like, the g of x function. Now, one thing I'm going to need is to calculate the period. So I can see the k value is 3, so therefore the period will be 360 degrees divided by 3, which is 120 degrees. Okay, now I'll start with the vertical scale here. I can see that the c value is 1, so that tells me the center axis here is y equals 1, so I'm going to put my 1 right in the middle. And then I look at the a value. So the absolute value of a is 4. So 4 is the amplitude. So basically the function goes up 4 from 1 and down 4 from 1. So if I add 4, I get 5. If I subtract 4, I get -3. So I know my vertical scale now. My period, I'm just going to draw one cycle. It didn't ask me to do any more, so I'll mark my 120 for the full period, and then I'll subdivide it into 4 equal quarters, because something exciting happens at the quarter intervals of any period. So if I divide that, that's 60, 30, and 90. Okay, and now I'm ready to sketch. So I know that this is it's a sine graph. So it starts off at the bottom here, and there's no phase shift, so I can make that a solid point, and I can go from there. I know sine starts in the middle, goes up, so it goes middle, maximum, middle, minimum, middle. And then I just make a nice smooth graph like that. And there's a sketch of what g of x looks like. Okay, second part says state the domain and range of f of x and g of x. So f of x, which is just the sine x function, the domain is always all real numbers. X is all real numbers. And the range, we don't have the graph here, but we know sine x and cos x go between -1 and +1. So I'll say y is any real number, but y is between -1 and +1. Okay, and g of x, once we've applied the transformations, the domain will not be affected by any transformation, so it stays at x can be any real number. And then the range, well, you can see from our graph now, because of the the c value being 1 and the new a value of 4, that we now have a minimum at -3 and a maximum at 5. So we can update our range to show that change. Y is an element of real numbers, and y is between -3 and +5. Okay. Now, part C says modify the equation for g of x to include a phase shift of 30 degrees to the right. Call this function h of x and apply the phase shift to the graph of g of x and transform it to h of x. Okay. So I'll do both. I'll do the equation and the graph. So the fact that there's a phase shift of 30 means my d value has changed from 0 to 30 degrees. So therefore the equation is going to be the same as g of x. So 4 sine 3x plus 1, but I'm going to add my d value in there. So it's 4 sine, put an extra layer of brackets here, 3. Now remember it's x minus d, so it's x minus 30 degrees, square bracket, and then the plus 1 that was already there. Okay, so that's the new equation, the new graph. Okay, so the axes, scales do not change. So 5, 1, -3. And I'll just do one period of this again. So I've got 30, 60, 90, 120. Okay, now if I do a phase shift, that means I'm basically taking, so let me zoom out a bit so I can see both graphs at the same time. I'm basically taking every point and I'm moving it 30 degrees to the right, directly to the right. So that point that was there is now here. The point at 30 degrees, which was the maximum, I'm moving that over to 60. 60-degree point at the middle now goes to 90. And finally, the minimum, which was at 90, is now at 120. Now, you notice the point at 120 goes to 150, but I don't have a spot for it on the graph. So that kind of falls off the graph. But because I've shifted everything over to the right, I've kind of lost my value at 0. But you can see the pattern here. The fact that it's 30-degree shift is nice because 30 degrees is exactly 1/4 of a period. So if I follow the trend here, if I go backwards, you can see the pattern. Min, middle, max, middle, and the next one would be min. So just by deduction, I can figure out that that point would be there. And now I can do my sketch again. Like that. Okay, if you compare them, well, they do look different, but it's just because it's shifted. Okay. So that's applying a 30-degree phase shift to g of x, create a new function called h of x. That's what the equation looks like. That's what the graph looks like. And you can see I didn't recreate this from scratch. I just took the existing graph of g of x and did a phase shift to it. Okay, 2 more examples we're going to do, and these are important. So example 2 is giving us some information about the function and the graph of the function. It's not telling us what the A, K, D, and C values are. It's giving us information that we have to use to get those values, and then being able to get the equation and of course do the sketch. So we're always going to do the sketch first, and then from the sketch we'll create the equation. Okay, so I'm going to read through this and we're going to kind of convert it, interpret what that means in terms of the parameters A, K, D, and C. So it tells us a sinusoidal function, so that says it could be sine, could be cos, has an amplitude of 3 units, so that tells us that the A value, well, it actually tells us the absolute value of A is 3, that's the amplitude. So A could actually be positive or negative 3, so we're not entirely clued in on what A is yet. K is 360 divided by the period, which they've just told us is 180, so that tells us K is 2. Now it gives us the maximum here, a maximum at 0.5, so that's actually 2 solid pieces of information. So I'm just going to put given there, so you know I just didn't pull it out of a hat. Now, here's where you have to use your logic. So I know that the maximums, I don't know why I put M, should say max. So the maximum's 5. I know the amplitude is 3. So I can kind of work my way down the vertical scale. If the maximum's at 5, if I go 1 amplitude below the maximum, I get to the axis of symmetry or center axis, basically the middle of the function, and that is my C value. So the C value is 5 minus 3, which is 2. Okay, and if I wanted to keep going, I could say, well, that makes the minimum. The minimum is going to be 3 below the C value, so that's 2 minus 3, which is negative 1. So I've got all that stuff. So you can see I've got A, K, and C. What I don't have is D, but also what I don't have is, am I going to use a sine or cosine function? So before we do that, I'm going to sketch what this looks like. I don't have to know which function I'm using yet. I know max is 5, middle center axis is 2, and minimum is negative 1. I know the period is 180. It told us that. So we subdivide the period into 4 quarters. So 90, 45, 135. Now the thing I haven't used yet is the there's a maximum at 0.5, so I haven't actually used that yet. I used the fact that the maximum was 5, but I didn't say anything about that point. So that gives us a first point on the graph, and that's important because it tells us where this function goes from there. Up till now I didn't really know. So again, this is one complete cycle, and I know the pattern as I go through the quarter periods. If I start with max, then the next quarter of the way through it's a middle value, then a minimum, and then back to the middle, and then back to the max. And you always know that a period begins and ends at the same value, same y value, so that seems to work. So now I'm going to do my sketch. like that. Okay, now we're going to create our equations. So my first equation, the first thing I have to decide is what base function am I starting from? And you always want to pick the one that's closest to what this graph is showing. Now I actually have four choices. So let me show you them here. And this applies all the time. Put one up there as well. Okay. Now you're probably thinking, well, I thought there was only sine and cos. So definitely that's part of it, right? So sine would look like this. Start at the middle, go up. So this is sine x. Cos x would start at the top, go down, and then back up. So that's cos x. Now the other two are just the negative. The ones, basically, if I reflected these vertically, flip them upside down. So in that case, the sine, if I flipped it upside down, would look like this. So this would be the graph of negative sine x. And if I flipped the cos x graph upside down, it actually starts at the minimum and goes up and then back down. So this would be negative cos x. So I have my choice of four different starting points. And it's kind of told us, well, a lot of times it'll tell you, give me an equation of this using sine and give me another equation using cos. So when it says sine, you could use sine or negative sine, it doesn't matter. Cos, you could use cos or negative cos. So let's look at this and see what it's closest to. Start with the most obvious. It's definitely our cos x graph. So I'm going to use cos x. And if I use cos x, I don't have to do any kind of phase shift because this is exactly the same as cos x. So when I use cos x, I also know that d is equal to 0 because there's no phase shift. Okay, so that will give me an equation. So now you can see I've got the function I'm using, cos x, the a, k, d, and c. Well, the d comes from here, the a, k, and c came from above. So that's an important point. Whatever my a, k, and c values will be used for both equations. It's only my d value and my initial function that will change. Okay, so in this case, my equation would be, I've got my, now about this absolute value of a equals 3, and I said, well, actually this could be 3 or negative 3. Well, whether it's 3 or positive or negative here depends on which of these functions you pick. If you pick sine x or cos x, the 3 is positive. If you pick negative sine x or negative cos x, your 3 is negative. Basically, the negative sign moves to the front and applies to the a value. So in this case, I'm just using cos x, so the 3 stays as a positive 3. And then I've got my cos function, which I've already said I would use. And then the k value is 2, no phase shift, so it's just 2x. And then the c value of 2 means I'm adding that. Oops, let's move that over a bit. So there's my first equation, and this is the most obvious equation. This involves no phase shift at all, and if you could do that, that's ideal. Now we have to pick another one, another equation, because it's said to represent the function with the equation in two different ways. So now I'm going to pick something to do with sine x. So I can either start with the regular sine x or negative sine x. So you could choose either one. I'm going to pick sine x. Okay. Now sine x, if I drew a sine x kind of just on top of here, I know that sine x would look like something like this. Okay, and that just comes down and back. Now what I want to do is I want to turn the graph of sine x into this graph. So basically what direction would I move this part of the graph to, and how many degrees do I shift it. So you can see I basically want to move this point to over here where the sine x graph kind of starts. So that would be a shift of 135 degrees, and because I'm moving it to the right, d is equal to positive 135 degrees. So I know what I need to do. I'm going to use sine x, and the d value is 135. So now I just use these along with my AK and C values from above, and now the equation looks like this. So now it's 3 sine, and now I'm going to have my 2 from my K, but now that I've got a D value, I have to put it in brackets with the X. So it's X minus D, which means X minus 135, square bracket to end it off, and then my plus 2 from before. Okay, so hopefully you can see the similarities. No matter what equation I make, it's going to have a 3 here and here. I could change the sign. The K value of 2 doesn't change, and the C value of 2 doesn't change. What can change is the sign of the 3, which in this case it didn't. The default starting point, whether it's one of these sine x, cos x, or negative sine x or negative cos x, and the phase shift if there is one. Okay, now I could actually make several more of these equations. I could have maybe used negative sine x as my starting point. I could have used negative cos x. And one of the things I didn't talk about is I could actually shift things to the left. I always try to do it to the right because it's just more obvious to me that way, but you can also shift things backwards. So your D value would be a negative value. Okay, one more question here. So this time, instead of just giving us information about the function, they've actually given us a graph of it. So basically same request. We don't have to do a sketch because the graph's already here, but we do have to pull out information about A, K, D, and C, or we could grab things like the amplitude or period and convert that into A or K. But basically we're kind of on an information hunt here. So the first thing I'm going to look at is I can easily find the max and min. So I'm going to write those down. So the max, the highest value, is 3. You can see that several times at these peaks. The min value is the values. The values are at -5. Okay, now here's a couple of nice little mini equations. If you know the min and the max, you can easily get the values of A and C. So the value of A and C, remember what A is. It's half the distance between the min and the max. So if I want the distance between the min and the max, I subtract. So I take the max minus the min. So that would be 3 minus -5, which is 8. So the distance from max to min is 8 units. But the amplitude's only half of that, so I divide by 2. So that'd be 8 divided by 2, which is 4. Okay, nice easy equation. Now the equation to get the C value is very similar to what we just used, except instead of subtracting these values, we're going to add them and then divide by 2. That's going to give us the average of the mixed max and the min, and the average of those points will be the C value. So 3 plus -5 divided by 2, that's -2 over 2, which is -1. Okay, so I've got my A and my C values, no problem. Now I need to get my K value, but in order to get my K value, I need to figure out what the period is. So how do we do that? There's several ways, but the best way is to find 2 maxes that are next to each other, or 2 mins that are next to each other, and find the difference between them in terms of degrees. Okay, so there's the first max, there's the second max, and I find the difference between them. So that's 90 degrees. That is 210. So 210 minus 90 gives me a period of 120 degrees. Okay. So as long as you've got two maxes or two mins on your graph, that's the approach you should take. Don't try figuring out stuff in the middle. You got a lot of cluttered stuff, like the graph is going up and down through there several times. This is much cleaner, is to do it through the maxes or the mins. The other thing you can do is, if you don't have two maxes or two mins on your graph, but you have a max and a min, you can find the distance between them in terms of degrees and then double it, because that would be the same as the period if you doubled that distance. Okay, so we've got our period, so now we can get our k value. K is 360 over the period, which is 120, so the k value is 3. Okay, now one thing I like to do is, once I get my c value, if it's something other than 0, I like to basically run a horizontal line through that value. Just let me try to do a nice straight line here. Okay, so it's only for really working out things like phase shift. Okay, if I need a phase shift, I might need to use that, because that's the middle of the graph. Sometimes people get confused and they use the x-axis as that, and it kind of messes you up, because you can see the middle values are along this line that I just drew, not on the x-axis. Okay, so I'm going to do two equations. The first one, I'm looking at this graph, and this is the first reason why that line is important. I can see that there's the center axis right there, and the graph that we have starts at the center axis and goes down, and I know from my four choices that's the negative sine x graph, okay, with no phase shift. It starts in the middle and goes down just like this one does. So I'm going to use y equals negative sine x, and with that I have no phase shift. So I've got my d value now, I've got my starting function, I've got my a, k, and c values. Now I just have to plug everything in to make my equation. Okay, now the a value is 4, but because I'm using negative sine x, remember I said that negative sign goes right in front of the a value, it doesn't stay in front of the sign. Okay, it would look weird, 4 times negative sine. It's negative 4 times sine. Okay, and then the k value was 3, so 3x, because there's no d value, so just 3x, and then the c value was negative 1. So that's the first equation. That's the best equation because there's no phase shift. Now if I was to do another one, which they've asked me to do, what am I going to use? Well, I want to use something with cos. Okay, so what does this, well, I could use either one. I'm going to use, I'll start with cos x. I know cos x, let me just zoom in a bit here. I know cos x usually starts right here where that dash was. Okay, now, so I'm going to say use y equals cos x. Now if I use y equals cos x, what's the phase shift for cos x to get to our graph? So normally cos x would start right here. At the beginning, it starts at the maximum. Our function has its maximum here, so what do I have to do to cos x to turn it into our graph? Well, I have to phase shift it from here to here. Okay, how many degrees is that? That's 90 degrees to the right. So that means, zoom back out, that means that my d value will be 90 degrees to the right, which is positive 90. Now again, I can go ahead and make my second equation. So now it's y equals, this time it's positive because I'm using y equals cos x, positive cos x. So it's 4 cos and then I've got my k value of 3. Now I've got a d value this time, so it's x minus d, or x minus 90. Make sure that's in brackets, closing bracket, and then minus 1. Okay, so that's how you go about that. Very, very important skill. Lots of practice in the handouts with the solutions that I provided. You can check your work. But once you know how to do this, you know, it comes pretty quick. It's just a process to extract the information and then decide, you know, what starting function am I starting from, and therefore what phase shift or d value do I need to use. Okay, so there could be multiple other equations that actually fit. If you ever want to check to see, you know, do these actually match this graph? Well, you can use an application like Desmos, plug these in, and see if they duplicate this graph. Okay, so that's it for today. In the final lesson, we will be looking at more application-based questions. So you will be using all the skills from this lesson and the previous couple of lessons to model actual real-life situations and come up with some very specific answers in terms of solving the equation for either, you know, the y value or the x value at a certain point. Okay, so that's it for today. Hope that made sense, and we'll see you on the next lesson. Take care.